Hi, my name is Richard Moore, and this is my Physics 2 Lab 4, Circuits. Introduction instructions. The instructions for this lab are to analyze the behavior of different circuits, the first of which being to evaluate the charge and energy conservation in series circuits, the second being to evaluate an RC circuit, observing how a capacitor charges, and the third being to evaluate the time-dependent voltage across a discharging capacitor. In order to perform these evaluations at all steps required, the lab instruction manual was to be followed, detailing a step-by-step procedure to follow and different values to calculate. Purpose. The goal of this lab was to predict the behavior of circuits containing resistors in series and parallel, examining the behavior of ohmic resistors and capacitors. Overall, though, the purpose of this lab was to learn more about circuit behavior, a topic that has been discussed extensively in class recently. Results preview. Through this lab, the behavior of 3 different circuits were analyzed and quantified in relation to voltage, current, and time constant, being Circuit 1, Circuit 2, and Circuit 3 as seen in these descriptions. The 2 pictures below represent the circuits created. Models and principles. The first model used in this lab was the resistance in series equation, which is R1 plus R2 plus ... plus Rn is equal to resistance in series. Next is Ohm's law, which is V is equal to IR. Next is the loop rule, which is the potential difference of a loop is equal to 0. The node rule, In is equal to I out, and the linearization equation seen below. Rationale. The resistance in series equation is used to determine the resistance in series of a circuit. The Ohm's law equation is used for the determination of circuit variables V, I, and R. The loop rule equation substantiates that delta V must be equal to 0, which is helpful in the process of measuring and determining voltages. The node rule assists in the determination of current, specifically the conservation of such, and the linearization equation is significant to the analysis of a time-dependent voltage across a discharging capacitor circuit, specifically in relation to RC. System and surroundings. The system in this lab was a circuit, including all components that relate to its functioning, and the surroundings was everything else near the experiment that does not include the circuit, such as table, chairs, and any other nearby electrical objects. Initial conditions. The initial conditions for this lab can be broken into 3 different circuits, being Circuit 1, Circuit 2, and Circuit 3. For Circuit 1, the initial conditions were the 2 1.5 volt batteries, multimeter, ammeter, voltmeter, a 47 ohm resistor, a 100 ohm resistor, and that the resistors are in series. For Circuit 2, the initial conditions are the presence of batteries, a 200 mF capacitor, and 2 light bulbs, first being a 10 ohm and then second being a 20 ohm. And for the third circuit, the initial conditions are the presence of batteries, the 200 mF capacitor, and this time a 30 ohm light bulb. Experimental data, Circuit 1 in series. The expected current can be found using the equation V is equal to IR, which determined that I is equal to 0.02041 amps. And the actual measured current, according to the node rule, was 0.01 amps. When the ammeter connection was reversed, the sign became the opposite. For the voltages, delta V net of the whole circuit is 0, which is used to calculate the voltages at every point. And for the true resistance, R is equal to V divided by I, which is performed for each resistor. When the voltmeters are placed on an ammeter in parallel with the 100 ohm resistor, the current reading will increase due to splitting. Experimental data, Circuit 2, the RC circuit. When the battery was connected to a 10 ohm light bulb and capacitor in series, the current goes to 0 and the capacitor charges. And when the capacitor was directly connected to the light bulb, the current goes to 0 and the capacitor discharges. The charge and discharge times for the capacitor of the 10 ohm light bulb is roughly 18 seconds to charge, 16 seconds to discharge, and the charge and discharge times for the capacitor of the 20 ohm light bulb is roughly 30 seconds to charge and 32 seconds to discharge. Experimental data, Circuit 3, time-dependent voltage across a discharging capacitor. Using the linearization equation seen below, we can determine that the slope of this, when graphed, is -1 divided by RC, from which we can find RC from the slope, which is roughly 9 seconds. To the right seen here is a picture of the circuit. Potential errors. The potential errors in this lab include timing errors, inaccuracies in the circuit setup, as not perfect connections could have influenced behavior, and the existence of resistance in the wires and circuitry components, including the ammeters. According to this what-if question, in a virtual experiment, the ammeter will have idealized resistance at 0, while in real life, the ammeter most likely has some resistance, affecting the behavior of the circuit. This rationale would then make the actual current lower than the virtually simulated current in accordance with V equals IR in inverse proportionality. And according to this what-if question, the actual experiment in real life has a higher capacity charging time than the simulated experiment due to the unidealized nature of reality. In the virtual experiment, there's no resistance in any component, when in reality, there is. And although it's very minimal, it increases the charging time, in part due to the V equals IR as in the previous question. Conclusion. Overall, the behavior of 3 different circuits were analyzed and quantified in relation to voltage, current, and time constant, being the 3 seen below. And the fundamental behavior of circuits and the process of quantifying such were learned about, granting a greater comprehension of the subject that will lay groundwork for future exploration in class. Thank you.